So what we're going to do today is we're going to study two random objects, and we're going to connect them through a geometric relation to express one through the other. This is joint work with my supervisor Zakhar Kabluchko and Christoph Thäle, and it will appear on the archive sometime maybe in the next 2 weeks, as it has been during the last 2 months. So yes, I don't have to do much because, as I said, I already did a lot. So when I say a simplex, I say it's a convex hull of finitely many points, and we have at most d+1 points in RD. That is something that we agree on. And what we are going to do is we're going to study random beta simplices. So what is a beta simplex? The points underlie the beta distribution. And we say that a point x follows a d-dimensional beta distribution. It has the density that you can see on the slides. It exists for beta strictly greater than -1. Why is this density interesting? You can get some very interesting special cases from it. For example, for beta to be 0, you get the uniform distribution on the unit ball. If you look at the weak limit from beta going to -1, you can actually get the uniform distribution on the sphere. And if you normalize it properly, you get, as beta going to infinity, the d-dimensional Gaussian distribution. And not just the special cases make this density interesting, but it also appeared in the work of Zakhar, Christoph, and Anna. They have published a series of papers on the beta-Delaunay tessellation, which is a generalization of the Poisson-Delaunay tessellation. And if you study this object, then what they were able to show is that the typical cell of such a tessellation is actually a beta simplex with an additional weight, which we will also introduce today. So this is also where this density turns up in, at least inside of mathematics, so you have an inside mathematics applications for it. So, like I said, this is the object we're going to study, so we have different points, at most d+1, and we don't need the beta parameters to be the same. So they are all from the same family of distributions, but they can be different beta parameters. So you can have some on the ball, and some maybe on the sphere, and some next closer to the origin. To visualize this density, I've created some pictures. So this is now a visualization of 4 beta points that have beta parameter 0. You can't really see from that picture that it's a uniform distribution inside of the ball. So let's go to polytopes, because simplices are of course always restricted to 4 points in at least the dimensions that we can visualize. So let's look at 400 points for beta to be 0. Now you can see that more or less we have this uniform distribution in the unit ball. We let beta go to -1, we can see that the points are now on the sphere. And we can also play around with the beta parameter a bit more. We can increase it and see what happens. It seems to be that if we've set beta to be 10, we are more densely around the origin. And if we increase it even more, let's say beta to be 100, we can see that it's very, very tightly around the origin. So one thing someone might conjecture is that the expected volume of such a beta simplex might be a monotonically decreasing function in beta, if all betas are chosen to be the same. And it's something that we may even be able to show today if we have the formula for the expected volume. So, this will be the goal for today. We want to find the expected volume of such a beta simplex. And how does one go about? What we're going to do is, first we're going to establish the geometric relation between simplices and parallelotopes. Then we're going to calculate the expected volume of a beta parallelotope, which will turn out to be very easy. We will then rearrange our relation cleverly, and then we will get an explicit formula for the volume of a beta simplex. So this will be what we're going to be doing today. And we're straight going to start with the first one. And we're going to start in 2 dimensions, the relation between simplices and parallelotopes. This is 2 points in R2, and this is the parallelotope that these 2 points span. The origin, I assume, is here in the left corner. And now if we connect these 2 points, this is the simplex that is spanned by these 2 points, which is just a line. And if we then draw in the height of this triangle, which can be taken as or formalized as the distance from this simplex to the origin, we can then see that the volume of the parallelotope is twice the volume of this simplex. So for 2 dimensions, you get this formula. And for 3 dimensions, I want to talk about 3 dimensions really quickly, because 2 dimensions is also always very easy, and you might get the idea better if you also look at 3 dimensions. And for 3 dimensions, we're going to look at the cube, because the cube is a little bit easier to visualize, and also any parallelotope can just be obtained by an affine transformation of the cube, and the volumes therefore relate to each other. And instead of drawing another picture, I actually have brought something three-dimensional, which is this cube. And you can see that it is colored, and if we just assume the origin to be the left-hand corner here, then the 3 points will be the other 3 vertices of the triangle. The simplex that these 3 points span is then the base of this triangle, and the distance to that simplex is the height of this triangle. And on the first glance, it looks like we might have 4 simplices that make up the volume of the cube, the parallelotope. But of course, when we're talking about surface area, we're talking about volume. So if you fold it up, you see that there's another simplex in here. And this simplex shares a base with the other simplices, but the height is actually twice of the other simplices. So this simplex, or this pyramid, has twice the volume of the others, and in total, what we then get is 6 times the volume of the simplex is the one of the cube. Now I'm going to pass this around, because it's nice to play around with, and to actually, I think if you had it in your hand once, you're not going to forget this relation anymore. Okay, and from this we can deduce that the general formula for dimension n will just be n faculty times the volume of the simplex, including the origin, is the volume of the parallelotope. Now, we would need to prove this rigorously, which we're not going to do today, because I think this suffices for you to believe me that it actually goes through, if you didn't know it already before, which I think many of you did, but it's still nice. Okay, this is good, because now we have the relation that we're going to need today, and next up, we're going to talk about the beta parallelotope. You can't break it, it's okay, don't play around with it. Nothing can happen. It's pretty sturdy, actually. Okay, so we want to turn a parallelotope into a rectangle. So we start with k points that are independent and beta distributed, and we define the parallelotope to be the Minkowski sum of the segments. And then, to find the distribution of this volume of the parallelotope, we're going to do some kind of Gram-Schmidt orthogonalization. So we're going to leave the first point as it is, and the second point will then be projected into the d-1 dimensional subspace that is orthogonal to the linear space created by the first vector. And we're going to keep on doing this for each iteratively, and basically what's happening is we have our parallelotope. This is the orthogonal space to the linear space of x1. We project x2 down, and then you can see that the rectangle that they create has the same volume as if we would take the upper right triangle and put it down to the left-hand side. So everybody probably knows that, and you can just do that iteratively and preserve the volume by projecting these points. So in total, we get something like this. And this is already very good, because we have some very interesting properties for the beta distribution. So 2 of these properties we will use if we have a beta distributed point and we take the orthogonal projection onto a linear subspace. Then we can have, when we have 2 statements, first of all, if we embed this projected point into Rk, using an isometry that preserves the origin and also preserves distances, the embedded point again has a beta distribution that relies on the original parameter and on the dimension where we came from and where we're going to. And another good property that we will use is that the squared norm of a beta distributed point is again beta. This time this is the classical one-dimensional beta distribution that you know with 2 parameters. And both of these proofs are straightforward calculations, and they actually make use of the rotational invariance of the beta distribution, meaning it only relies on distance and not the exact position.
Sorry, IL is the embedding, you said?
IL is an isometry into Rk. So I'm sorry, I haven't specifically stated that, but we will use this isometry some more times. It preserves the origin and it also preserves distances so that we don't destroy any volumes that we want to project it to. Okay. So in particular, we need this isometry, so this is again beta in Rk, because otherwise it would just be in Rd still. Okay, and now we use these lemmas because the relation that we've established will now let us state that if we square the volume, we just have the product of independent one-dimensional beta random variables. And that's very great, because this already concludes the second step. We've calculated the volume of such a beta parallelotope, at least in distribution. Okay, so what we have established this far. We take d+1 points and Rd+1. They each have different beta parameters. we have denoted the affine subspace that is spanned by these points by A, and we have denoted HA in the picture as the distance of this affine subspace. And then, if we start with the parallelotope in D plus 1 dimensions, then we use our relation that we have established before, and then we use the base times height formula for such a simplex to draw out the height, and we get this dimensionality constant, which cancels out with the faculty before, and in total we get this relationship. And you might think that we would already be done, but then my talk would have been too short, so we still have, of course, one problem that we need to solve. And the problem is that h of A and the volume of this simplex are surely stochastically dependent, because as you can see, we have A is just as the affine space created by the points, and the distance to it is surely stochastically dependent. So this is where we need to do some more work, and what I meant with rearrange cleverly, because we're going to need another statement, and this statement is originally due to root min miles. Now this might look like a lot, but actually the first part is just what I've introduced on the other slide, so there's nothing new here. And what is new on this slide is the statement that this affine subspace intersected with BD is almost surely a k-1 dimensional ball that has this radius. And what we're going to do is we're going to embed our original points, and we're going to rescale them by this factor, such that they are, of course, again, in the ball of k-1 dimensions, because we want them to be beta distributed again. Now, let us look at another picture, which makes it a little bit easier. We have our three points. This is the intersection of A with the ball. And you can see that it's some kind of circle. And now, the distance to that circle has been denoted by h of A, and then you can just use the Pythagorean theorem to find that the green line is square root of 1 minus h squared of A, because, of course, the intersection ends at the unit ball, which has radius 1. So this is why we scale with this factor. Okay, now we haven't had the statement of the lemma. So again, this is nothing new, just a preliminary from the previous slide. The first statement is that the joint distribution of Z1 and Zk and the distance, or any function of the distance, are actually stochastically independent, which is good, because we're going to need that. Second of all, we actually get the joint density of these points, and it seems to be a product of the original beta densities, but with an additional weight. That is just the volume of the simplex spanned by these points to some power. And why this turns up, we will see on the next slide, but first of all, the second to the last statement is that we also get the distribution of the distance to the subspace, which is, again, one-dimensional beta, relying on dimension of the points. Now, where does this weight come from? The answer is the affine Blaschke-Pitcairn formula, which Daniel has already introduced, at least in 2 dimensions, and this is just the general version in dimensions. So this is good that he introduced it, because in particular, I don't need to introduce these measures, because he already has done that. Just as a reminder, this is the Lebesgue measure, and this is the measure on affine subspaces. And what this formula then allows you to do is you have an evaluation of the integral in k points in Rd, and you can write it as an integral over the lines and evaluate it, but you need to add this additional weight, which is the value of the simplex. As you remember in Daniel's formula, this was just the distance, which is equal to the line in 2 dimensions, and now we get the volume of the simplex. Okay, so this is what we're going to use in the proof, and I'm just going to sketch it because the proof is not very nice. There's a lot of integrals and a lot of substituting, and it probably will be the point where I'll lose you all, not because it's difficult, but because it's very boring. So, I'm just going to sketch it. What we do is we take test functions phi and g, and we're going to look at the expectation of the product of both. This is proportional to this statement. So all we have done is just plugged in the densities of phi and also the definition of the z points. And now what we do is first we use the affine Blaschke-Pitcairn formula on this integral, and then we're going to substitute twice. And the substitutions are not really that's hard to see, because they are exactly the ones from the preliminaries. First we embed each xi into Rk-1, and then we rescale by this square root of 1 minus h squared of A. And if we do all that, we get such an expression, and now we have 2 integrals that are separate from each other, we can see that this one is, gives us exactly the density that we had before, where again the weight came from the Kabluchko formula. And up there we have gathered all the terms in this gamma, which came from substituting 2 times. And you can already see that this looks like another beta density. So what we do is then the product structure gives us the independence. If we set G to be 1, we get that we get the second statement over the over this density, and doing the other thing respectively gives us the density of this. So this is the sketch proof of it. And what you might notice is that even if we choose the maximal point K to be D, the canonical decomposition states actually that the D points distributed in their own affine Hall are no longer independent, but rather they have this weight turning up. So since whenever we apply this canonical decomposition, such a weighted simplex turns up, this actually motivates us to introduce them as an object. So again, the preliminaries are mostly the same, and if we say that these points have this joint density, where rho is now just any number larger than -1, then we say that the convex hull is a beta simplex that relies on the dimension, at the parameters, and at the weight of the simplex to the power of rho. And this, as I've alluded to earlier, is also the object that turns up in the beta-Thäle tessellation. So this is exactly how the points are distributed, how the typical cell of this beta-tessellation is distributed like this object, which makes it even more interesting to actually introduce it. And we can do the same for beta-parallelotopes, because we're going to need this in the next proof. And again, this time we weigh by nabla to the power of alpha, which is just the volume of the parallelotopes, and then we get the analogous definition of it. Okay, and for these new objects, we can actually prove the same canonical decomposition as we had before. So if we now take a beta parallelotope, makes the definition a little bit shorter, and we have the same preliminary as before, we can say, again, the random vector z1 to zk and h squared of a are stochastically independent. The convex hull of the points that are projected is again a beta simplex, and h squared of h has a beta distribution, but now this rho turns up in the first parameter of the beta distribution. Now, why is this again a beta simplex and not a beta parallelotope? The answer is again this geometric relation, because we would start in the proof with this density, but now we can write the volume of this parallelotope as volume of the simplex times distance to the power of rho half. And this then explains, first of all, why we end up with a beta simplex, and second of all, how this rho arises in the beta distribution. Okay, and now we have everything to actually prove the moments of the volume of a beta simplex. And we're going to prove an explicit formula for this. So this is the goal. We want to have points x1, xt plus 1 in Rd that are not weighted, so we want to have independent points. And for this we need to start, of course, in Rd plus 1 and 1d plus 1 points, because we're going to start with the beta parallelotope. And then we're going to go down 1 dimension to actually have d plus 1 points in Rd. So we start with such a beta parallelotope. This is now volume weighted with the power rho. We again denote the affine hull by A, the affine hull of the points by A, and the distance by h of A. And we introduce the rescale points, Zi. And now what we have is, we have this volume is equal to this volume, which is just a geometric relation from the beginning. We then can embed the points into our D, which will not change the volume because the asymmetry preserves distances. And then we can draw out, we can just write these points as Zi, and for this we have to draw out square root of 1 minus h squared to the power of d. So we end up with this relation, which is this one. And now, the canonical decomposition gives us everything that we need. Because, first of all, we know that these and these are independent, which allows us to take the expectation and separate the expectations. We also know the distribution of the right-hand side, which is almost the distribution, sorry, almost the object that we want. But now we have, of course, this rho plus 1, which came from the canonical decomposition. And we have the distribution of h squared. which is this one-dimensional beta. So we can separate take expectations, separate the expectations, and since we're going to study moments, we're going to introduce the parameter for the moments, which is going to have to be larger than 1/2. And rearranging them, so putting everything on the left-hand side, gives us this. And the left-hand side of this is actually explicit because sorry, the volume of the parallelotope has been identified earlier to be the product of beta variables. And h squared is this beta distribution. And of course, all moments of this distribution are already available. So we can just plug it in. And finally, this then leads to this formula. Now, everyone except maybe Dominic, since we talk about gamma functions, is going to be disappointed at this point, or might be disappointed at this point. But first of all, what we can do to make this a little bit more concise is let rho go to -1. Because as you remember, this is a beta simplex weight to the power of rho plus 1, and we wanted to have to the power rho of 0. Letting rho go to -1 gives us this formula, which is a little bit more concise. We would need to argue the convergence and distribution holds, which follows from the beta distribution converging as it goes to -1, and then everything is bounded because we have volumes inside of the ball, so we can apply dominated convergence. And this then gives us that the expectations converge and gives us this formula. And it looks a little bit nicer, first of all, but like I said, on the second glance, it's actually very nice because all we have are gamma functions, or products of gamma functions, or quotients of gamma functions, and all of these are very, very easy to study. So what we can do with this is that we can, first of all, now show that the volume is actually monotonically increasing in beta if all beta are chosen to be the same, which we have conjectured at the beginning. We can also get condensed forms, such that if we all choose them to be 0, which is the uniform distribution on the ball, we can write this as a product of these binomial coefficients. The formula is originally used to Kingman, and we can just recover it using our approach. And we can actually also use it to calculate the expected volume of weighted simplices, which then will come in handy once one studies the beta-Thäle oscillations. And the last thing one can do, or what we have done in the paper, we can actually show mod Gaussian convergence of the log volume. And this then gives you a CLT and precise asymptotics. So that's very easy. You just take the sum, you separate the parts, and then you have the asymptotics for the gamma function. You can use Stirling's formula or other theorems to easily show the asymptotics of these expressions. And there are more things that we've done in the paper, which you can look up maybe someday. And that's all.